Okay, this is going to be the last section here. This is going to be over section 12.12. It's also going to cover 12.13 and 12.14, though much of that is just going to be extraneous reading if you would like to go through it. The Doppler effect. The Doppler effect is going to be the frequency shift that occurs when a listener is in motion relative to a source of sound. The source and listener frequencies F sub S and F sub L and their velocity components are related with the following. The frequency of the listener, and then you've got the ratio here of the velocity plus the velocity of the listener divided by the velocity of the sound waves plus the velocity of the source times the frequency of the source. The other things that we will be talking about are the importance of acoustic principles. What is important about it? Well, animals such as bats can locate insects, and dolphins can navigate using ultrasonic waves. They also have uses, medical uses, to break up kidney stones. You can also use them in evaluating pregnancy, how that's doing. The reason you would use ultrasonic imaging for a fetus is you don't want to use X-ray imaging, because if you start X-raying a growing fetus, you've got a lot of cell division going on in there, and X-rays will play havoc with that. You're going to cause the baby to maldevelop. They're not going to develop as they should, so you don't want to do that. Instead, ultrasound is the better way to go. When it comes to musical tones, there are many tones that contain different frequencies, and depending on how an instrument is plucked or bowed or struck, or how the column of air vibrates, you can have a fundamental frequency and many harmonics at the same time. That may not necessarily be something that you want to hear. And two tones may have the same fundamental frequency but sound different because of the presence of different intensities of the various harmonics. One may have more harmonics in it than the other, and that's going to maybe cause a difference there that you didn't want. So let's take a look here at the Doppler effect. Okay. Obviously, when an ambulance approaches you with its sirens on, then it seems to drop as the vehicle passes. That is known as the Doppler effect. When the source of sound and a listener are in motion relative to each other, then the frequency of the sound heard is not the same as the source frequency, and you can work out the relationship between the two. So we're going to consider a special case in which the velocity of both the source and the listener lie along a line that joins them. We'll take this line to be the x-axis with a positive direction to the right, and assume that the source is to the right of the listener. So we got the source here, it's to the right of the listener. So you got a guy who's listening to the radio here. You've got law enforcement over here that's hearing that. You got a line that's drawn between them. And this coordinate system is at rest with respect to the air. So we're going to let V sub S and V sub L be the x components of the velocity of the source and listener with respect to the coordinate system. And thus the direction from the listener to the source is going to be in the positive direction for both VS and VL. Okay. The speed of sound is always considered positive, but V sub S and V sub L can either be positive or negative because they're components of velocity. If V sub L is greater than 0, the listener is moving to the right. If it's less than 0, then it's moving to the left. Same thing with V sub S. So let's think first about a listener moving with velocity towards a stationary source. The source emits a sound wave with frequency F sub S and wavelength V divided by F sub S. The figure shows several wave crests separated by equal distances of a wavelength, lambda. The waves approach the moving listener, and they have a speed of propagation of v plus v sub L relative to the listener. So the frequency with which the wave crests arrive at the listener's position is going to be this. We're going to take this expression and we're going to change it a little bit. We're going to add v and v sub L. And then if we take this, substitute it in for the frequency, the stationary frequency, then we get a ratio here. Then we, rather than have a velocity by itself, we're going to augment that a little bit. We're going to have something that's a little bit greater than 1. So what you're going to end up with is something here that's a little bit greater than what you're actually hearing here. So if the listener was moving away, then the pitch would be a little bit lower. If the source is moving, the wave speed relative to the air is still considered to be v. It is determined by the properties of the wave medium and is not changed by the motion of the source. But the wavelength is no longer equal to this. The time for emission of one cycle of the wave is the period. And during this time, the wave travels a distance of the velocity times the time. And the displacement of the source is going to be this. The wavelength is the distance between successive wave crests and is determined by the relative displacement of the source and the wave. So we've got moving away, then we've got this guy who's still walking towards. So it's going to be different in front of and behind the source. In the region to the right of the source, this is the wavelength that's going to be heard, because now we're taking into consideration the velocity of the source. In the region to the left, this is going to be the wavelength. So to find the frequency heard by the listener, we're going to make these particular adjustments, and then we end up with this particular ratio right here. Here is an example of the Doppler effect and its applications as far as meteorology goes. You can see the different colors here corresponding to the different speeds and, of course, the direction. And usually, I know here in the South, whenever you start to see different colors coming together in a very small spot, that is considered to be a rotation, a funnel rotation, and the name hook echo seems to be now in common parlance among a lot of meteorologists. But it's important because it lets people know that something dangerous is coming, even when you can't walk out and see it. So some of the applications of acoustics, I think we had gone through, blasting out kidney stones rather than trying to go in and to operate on them. Here's a nice description of that. You can also see where animals sometimes go through and will use different returning echoes. Will let them know what their environment looks like immediately. So lots of good applications there. And then finally, for musical tones, the pitch of a musical tone is going to be the perceived frequency. For middle C, you're looking at something around 262 hertz. That's considered to be on pitch. An octave above that, it corresponds to twice the frequency. 2 octaves above middle C, you can see the frequency there. So depending on the presence of different intensities or various harmonics, we can say that certain musical tones sound pleasant or not pleasant. That difference is going to be called the timbre. which is often described in subjective terms. And then we've got a discussion here regarding different frequency ratios between certain notes, like a C to a G has a frequency ratio of 3 to 2. It's considered to be a perfect fifth. C to E, 5 to 4 is a major third, and so on and so forth. So these musical terms that you actually hear do have a physics description that goes along with them. If we want to be able to play major triads starting on various tones on a keyboard instrument, such as piano or organ, complications do arise. Either we add a lot of extra keys in each octave to get the exact frequencies that we need, or we compromise a little bit. The most common compromise in piano tuning is called equal temperament, in which every pair of adjacent keys, white and black, is tuned to the same frequency ratio of 2 to the 1 over 12. And this interval is called a semitone or a halftone. A succession of 12 of these then forms an exact 2, or 2 to 1 octave. The perfect fifth is 7 semitones. The corresponding frequency is 2 to the 7 over 12. This ratio is close to the ideal of 3 to 2, or 1.5. But if you're sensitive enough, you can hear the difference. I'm not so sure I'm skilled to be able to do that. But anyway, there we are. So those are some applications of a lot of the wave theory that we've seen up to this point.